Hi, my name is Linda, and I'm a member of the Lethbridge High School cGEM team of 2020. This year, our project is called T-pectinase, which stands for Targeting Pectin to Accelerate Compost Enzymatically. As you probably know, we humans produce a lot of garbage, and much of what is wasted is actually food. Landfills have been growing exponentially with many items being compostable food waste. As food rots in landfills, it releases a large amount of methane gas, which is an extremely harmful greenhouse gas that plays a factor in causing global warming. While some households do at-home composting, this solution can attract pests and may interfere with people's busy lives, so it isn't that popular. And even though there are composting facilities and food waste disposal services out there, oftentimes they aren't readily accessible. And here are some statistics around food waste in our city. As you can see from the pie chart, about 48% of what we throw away in our city is actually organic material, stuff that could be composted. Additionally, you can see from the graph on the right that our city's overall waste compared to Alberta and Canada, we as a city make more waste per capita. From learning about these statistics, we confirmed that the need for waste diversion and composting is clear. To learn more about waste diversion and composting as well as its presence in our city, our team set up a virtual interview with the City of Lethbridge's Education and Community Initiatives Specialist in Waste and Recycling, Nicole Robinson. Through this interview, Nicole made us aware of one of the largest barriers the city's education team has in reaching out to people in the community and spreading their message. She expressed that it's been hard to get people to care about waste diversion methods like composting. This confirmed that our team's first steps should be in reaching more people and getting the message out there of why food waste is such a problem and how we can begin to improve this problem. In order to raise awareness about the problem of food waste, our team has been working on doing outreach in quarantine. In May, we hosted a virtual music recital over Zoom featuring members of our own team, as well as some guest performances. We did this in order to shed light on the problem we are tackling, the problem of food waste, and to introduce our project to the public. Additionally, we are in the process of creating a YouTube channel focused around our project. So while the focus of our human practices and outreach has been to learn more about composting and to spread awareness of reducing food waste, on the biological side of our project, we are focusing on finding ways to increase the efficiency of composting using synthetic biology. A major aspect of this system is pectin. Pectin is a complex family of polysaccharides found in the cell walls of vascular plants, as well as in the cell walls of other organisms like algae. Because pectin is present in the majority of the aspects that make up a compost pile, like upper fruits and plants, targeting the breakdown of pectin for our system will increase the rate of the breakdown of compost. There are a variety of pectins, which may vary in complexity, but the one that is the most abundant in nature is homogalacturanon, which is commonly abbreviated as Hg. Hg forms the backbone to most pectins and is the simplest form of pectin. In our system, we chose to target the breakdown of this pectin because of its commonality and structural simplicity. In order to achieve our goal, which is to increase the rate of composting, our system is based on providing the enzymes that follow the degradation pathway of Hg. We selected the enzymes to do this job from the organism Paenobacillus amylolyticus. Now I'm going to hand it over to my teammate Thomas to tell you more about our system.
So why did we choose PNL, PEL-B, and PEL-C? Well, firstly, these three enzymes have quite a wide substrate range, meaning they can break down both methylated and unmethylated homogalactran. Secondly, these organisms can break down homogalactran without a methylesterase, meaning they can break down homogalactran without having to modify it first. This is beneficial for us because it skips an entire step of the degradation process. Thirdly, PEL-B is very, very good at breaking down unmethylated homogalactran, and it's almost as good as PNL, PEL-A, PEL-B, PEL-C, and PEL-D combined. On the flip side of this, PNL is really good at breaking down methylated homogalactran, so you can see how these two are a natural pair. Finally, PEL-C allows PEL-B to access the internal unmethylated regions of homogalactran, which is necessary for the complete degradation of the polysaccharide. Originally now, we were planning to use these three enzymes as well as PEL-A and PEL-D. However, a paper from Kegi and Duran said that, quote, PEL-A and PEL-D could be omitted from the enzyme mixture without compromising the rate of deconstruction or the final degree of completion. And this slide from figure 4 of their paper reflects that data. You can see that the three enzymes we're using are just about as effective as the five enzymes, as using all five enzymes. So for simplicity's sake, we'll just stick with PNL, PEL-B, and PEL-C. Now, for system delivery, we have two different methods that we can use. Firstly, we could put the pathway into a microbe and then apply the lysate to the compost, or alternatively, we could purify the enzymes and create a lyophilized powder. Currently, we're leaning towards the first option as it could create a higher yield, although we're still undecided. Now, for what we'll use to transform and express our system, our hosts, we're we're deciding between two options. Firstly, we have E. coli. It has rapid growth and high protein yields. It's a classic for a reason. Additionally, it has the added advantage of its genome does not include any pectin degrading enzymes. This is useful for us as it allows us to just test the efficacy of our system without our host getting in the way. Alternatively, we have Bacillus subtilis. Now, one advantage that Bacillus subtilis has is that it's classified as safe and not considered pathogenic to humans. This is advantageous as if we're planning to sell this, people may be hesitant about, bringing something pathogenic into their home, and just generally having our system not be pathogenic when we're putting it around people is useful. Uh, However, there is a quirk to it. Pectinases may be present in its genome as it uses polysaccharides as its carbon source. Now, this actually may be helpful to us as it may actually increase the efficiency of our system. However, it may make it hard for us to see exactly how well our system is doing at breaking down homogalactronate. Now, I'm going to talk about human practices for a bit here. Now, the most common piece of feedback we've got in all of our human practices in interviews is that the industrial sector is probably a better market to sell to than the individual consumer. Now, this is for a few reasons. Firstly, since the industrial sector is doing so much more composting than just your average consumer, they will have a higher need for something that increases the efficiency of their composting. Uh, another Another reason is that it may be hard to, get our project out there to the home gardeners, the home composters. The marketing of our project may be difficult. However, if we were to just partner with a municipal composting facility, that issue would be alleviated. Thirdly, the it may be easier to it may make the retail easier as it may be hard to get our project onto store shelves. And again, partnering with like a municipal composting facility may alleviate that image. Now, we talked to Bill McMillan, a waste and recycling engineer for the city of Lethbridge, and he also expressed some concern about the uncontrolled conditions within our composting system, especially regarding thermostability. He said that, quote, it could have a big impact if your project can be developed to control the compost environment so that it remains ideal for its intended purpose. Now, unfortunately, it is a bit out of the scope of our project to control the temperature of the compost. However, it is important to remember that our system will not be working under ideal lab conditions all of the time. So with that in mind, we are working on a protocol to improve the thermostability of our system. We'll do this by introducing point mutations into our enzyme with the aim of making them more stable. We've completed the first step of this pipeline, which is homology modeling, but we're still currently working on the rest. Now, as you can see here, we have these models of PNL, PEL-C, and PEL-B. And again, uh, well, that interview with Bill McMillan really taught us that we do need to improve the thermostability of our system. And if we want it to work, it's going to need to be able to survive in the different conditions that composting will be taking place under. Now, finally, I'd like to talk about how we plan to scale up our system. So we're going to focus on the lysate delivery method for the industrial application, as if we were to partner with a municipal composting facility, they would need a fair amount of our project. So we plan to provide this by growing our cells in a fermenter and then lysing them. This is far more efficient than purifying many enzymes, and this will hopefully allow us to produce our system in the quantities that the municipal composting centers require. Finally, I'd like to thank our primary advisors, Dr. Laura Keffer-Wilkes and Jaleese Heller, as well as our student advisors Luke Seville, Dia Couponces, Damon Larosa Montes, and Christy Turton. as well as MindFuel, the University of Lethbridge, RD, Geekstarter, Biotrex, IDT, and iGEM. Thank you so much.